अगले अटैक में।
Hey guys, this is CHEMPLIFIED and today we will talk about Heisenberg's uncertainty principle. So let's start with the statement. According to Heisenberg uncertainty principle, the exact and simultaneous determination of position and momentum of a moving microscopic particle is impossible. So remember these terms: exact, simultaneous, right? The exact and simultaneous determination of position and momentum of a moving microscopic particle is impossible. What is the meaning of exact? We all know the meaning of exact. What is the meaning of simultaneous? Simultaneous means together. You cannot find the position and momentum of a moving microscopic particle together or simultaneously in one instant, you can say, right? So Heisenberg uncertainty principle simply states that it is impossible to find the position and momentum of a microscopic particle simultaneously. All right, for this particular statement, this relation was given. The relation is delta p dot delta x is greater than equal to h by 4 pi. Now what all this means? Delta x means error in measurement of position, and delta p means delta x is error in measurement of position and delta p is error in measurement of momentum, and h is Planck's constant, right? So this is the relation. Delta p dot delta x is greater than equal to h by 4 pi. Now what is the significance? How this relation works? Let's see that. Let us suppose that we know the exact mass and velocity of a microscopic particle. Let it be any particle, electron or photon, any particle. We know the exact mass and velocity of that particle. We are supposing that, all right? We are supposing that we know the mass and velocity of a microscopic particle. It is a hypothetical condition. If we know the mass and velocity of a microscopic particle, we can calculate the momentum using the formula P is equals to mv, right? We can use this formula to calculate the momentum. Now since we can calculate the momentum, if we calculate the momentum, delta P will be equal to 0. Why delta P will be equal to 0? What is the meaning of delta P? Delta P is the error in measurement of momentum, right? But since we know the exact mass and velocity of the particle, we can calculate the exact momentum, right? Since we can calculate the exact momentum, it simply means delta P will become 0, right? I hope this is clear till now. Now what will happen if delta P is 0? Now again come back to the relation. We know the relation of Heisenberg uncertainty principle. Delta x dot delta P is greater than equal to h by 4 pi. Now in the previous stage we calculated that delta P is 0, right? So now substitute delta P is equal to 0. You will get delta x dot 0 greater than equal to h by 4 pi. Now what will be the value of delta x? Delta x is greater than equal to h by 4 pi dot 0. Let me calculate in a different manner. delta x is greater than equal to h upon 4 pi delta p. I can do that mathematically. I just bring delta p to the other side, it will be in the denominator. Now we know the value of delta p. Delta x will be equal to is greater than equal to h upon 4 pi dot 0. If you multiply anything with 0, it will become 0. You will get delta x h upon 0. Now let me move it a little bit. If delta x is greater than equal to h by 0, now what will happen to this side? Anything, if you divide anything with 0, it will give you infinity or not defined value. Here we will use the term infinity. So delta x is greater than equal to infinity. Why? Because when you divide h by 0, it will give you infinity. So what is the meaning of this? It means delta x is error in measurement of position. Is infinite. It means error in measurement of position will be infinite. If you know the exact momentum, then delta p will become 0. As soon as delta p is 0, delta x value will be infinite. So now look at the relation again. This was the relation. If you know delta p is 0, then delta x will be infinite. And change the situation. If delta x is 0, if you put delta x is equal to 0, then delta p will become infinite, right? And the symbol, look at the symbol, it is greater than equal to. Delta p will be greater than infinite. That's how Heisenberg uncertainty principle works. If you calculate the momentum, error in position will be infinite. If you calculate the position, error in momentum will be infinite. That's how Heisenberg uncertainty principle works. Now what is the significance, what is the role of Heisenberg uncertainty principle? In Bohr atomic model, you can read it. I have written the formulas. In Bohr atomic model, Bohr gave the formula for radius. Bohr calculated the radius. Radius means he simply calculated the position of electron in nth shell, right? Bohr calculated the position of electron in nth shell. He also calculated the velocity of electron in nth shell, and we know the mass of electron is 9.1 into 10 to the power minus 31 kg. Now using the velocity term and the mass term, we can calculate momentum. P is equal to mv. Since we know the exact velocity and exact mass, the momentum will also be exact and delta p will be 0. And according to Heisenberg uncertainty principle, after calculating the momentum exactly, you can never calculate the position. The error will become infinite, right? But Bohr calculated the radius. So in one way, Bohr calculated the position and momentum of electrons simultaneously, which is not possible according to Heisenberg uncertainty principle. So Heisenberg also helped in providing one of the limitations of Bohr atomic model. Now how this works, let's take a look at that. Now we will try to understand how this process works. Now electron is very small particle. To calculate its position or velocity, you have to emit radiation on it, and that radiation is in general terms known as photon, right? So when a photon is radiated or imparted on an electron, it get deflected after striking the electron, and that deflection is observed in microscope. That's how you calculate the position or momentum. Now we all know that photon is a moving particle, so it carries kinetic energy. Now after it strikes the electron, it transfers some of its kinetic energy to the electron. As soon as it transfers its energy to the electron, the position and the momentum of the electron changes. Position and the momentum of the electron changes. We can only reduce the change in position or the change in momentum by changing the wavelength by small wavelength or long wavelength. Small wavelength means frequency is high, long wavelength means frequency is short, frequency is low. So as soon as the photon hits the electron, its position and direction changes. For example, photon is hitting it in this direction. After striking, the electron will change its position. It will leave the path it was following, right? That's how it works. For example, you have taken a wave of high frequency. High frequency wave means short wavelength. High frequency short wavelength, lambda. High frequency means short wavelength. Now high frequency will result in accurate position because it's fast and it will instantly give you the position. Most accurate position will be found out by high frequency. Now suppose if you are using low frequency or long wavelength, high wavelength you can say. Now this will provide accurate momentum. This will provide accurate momentum, but it will change the position. Understood? Right? That's how you calculate the position or momentum of a microscopic particle. In this case, we are talking about electron. Right? So this was your Heisenberg uncertainty principle. This will be it for today's video. Thank you very much.